Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Marzia Parisi with us today. Hello, Marzia.
Hello, Frank.
How are you doing today on this June 18th of 2024 as we record this?
I'm doing pretty well. How are you?
I'm doing awesome. Where are you located at? What's your geolocation?
I am in Pasadena, California.
Ah, okay. June gloom happening?
Yes, actually, I live in LA and it's kind of hot over there. And then drove to the mountains here and it's kind of gloomy. So
Yes, yeah. Traditional. Very good. Cool. Very nice. And I, of course, am in Phoenix, Arizona, and we are definitely into our triple digit Fahrenheit, 40, 41 centigrade kind of stuff. And so it's good and toasty.
yeah, I imagine.
You learn to do stuff very early in the morning when you live in the desert. And
Yeah, I always forget that you're on the same time zone that we are.
this
When?
of year. So half of the year we're in the same time zone as California. The other half we're in the same time zone as Denver. So yeah, Arizona never changes time zone. So which I think is a good thing, but what do I know? Very cool. And Marzia, what do you like to do for research?
Right. So I study the outer solar system. So I have actually done some work on inner solar system as well, but mostly my passion is, from Jupiter onwards.
Cool. The gas giant.
Yeah, the gas giants, the ice giants, icy moons. So my background is gravity science and
Oh,
radio science in general.
okay.
So I studied the interior of planets and satellites, looking at their gravity field and rotation and tides and so on.
Nice.
I also like to look at atmospheres. You can learn a lot about atmospheres from gravity as well.
Mhm.
And then you can learn about atmospheres also, with radio occultations, which is part of radio science. So yeah,
Yeah,
that's
cool.
all. That's what I do.
Very nice. Beautiful. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Uranus Orbiter and Probe, a radio science investigation to determine the planet's gravity field, depth of the winds, and tidal deformations. Marzia, take us away.
Yeah, thank you. Yeah, so first thing first, I want to acknowledge my co-authors. This is JPL. Um, it's full of JPLers in this article. So, it's obviously a concerted efforts between people that do science and people that do more like mission designs, orbit design. So.
Cool. Nice team.
Oh, yeah, as you may have heard, maybe Uranus has been proposed just casually right, on the Planetary Science Decadal Survey as the next target for NASA large missions. And so there's been a lot of excitement since then. And in this paper, we try to basically determine what we would need to do a gravity science investigation at Uranus.
Yeah.
So in this paper, particularly, we focus on the planet.
Mm-hmm.
So there's a lot of interest on the moons as well, right?
Oh, yeah.
But this paper in particular focuses on the planet itself.
In body.
So,
Yep.
yep. So, Uranus is an ice giant. It's around 20 astronomical units from us.
Mm-hmm.
Average, maybe 19, still very far. And we only explored it with Voyager 2 once in 1986.
Yes.
Yeah, so we don't know a lot about the planet. We did one flyby. It was kind of far away. 80,000 kilometers above the surface. So we did get some information, but, it's one flyby and everybody has been excited to go back. So yeah, so in this paper, we explore what we know, in the introduction, we're kind of saying, well, we do have a few of the parameters that describe the gravity field, the magnetic field, the rotation of the planet, the atmosphere.
Right.
obviously, as it always happens with space missions, the Voyager 2 opened a lot of questions that now we are, looking forward to answering. And so in this case, what we're thinking is obviously nothing is set in stone, but we're thinking about orbiters. So we are basically riding on the of what we learned from Cassini, the Cassini mission at Saturn, and then the Juno mission at Jupiter, right? Like these are missions that so Cassini obviously was before, because I believe that the Saturn orbit insertion was 2004, but then actually Juno and Cassini ended up doing this very close orbits to the planet at the same time, because Cassini was 2017 and Juno was started in 2016, right? So since 2016, we have learned so much about gas giants. I mean, we even just looking at the images that we got from Cassini and Juno, I mean, we've learned so much, right? We have completely new picture of Saturn and Jupiter, right?
Yes.
So we're kind of hoping, to do the same thing at Uranus.
Yes.
And we know we have, very few close images of the planet. There is a lot of ground observation going on, of course, but it's different when you get so close to the planet, right? So for Uranus, for example, you imagine it like such a smooth planet. It's this blue ball, right? So I mean, if you think about Jupiter, right? I mean, we of course knew about the belts and zones there, but we didn't know what was going on at the poles, right? So there are these images from Juno that are just breathtaking, where you see the poles and you see completely different planets. So we're hoping, that something very similar, will.
Discoveries.
Yes, we are hoping that something very similar will happen. Yes. And so obviously, multidisciplinary studies are very important. So gravity science is not standalone, right? It's really important for studying the interior, but it goes hand in hand with, for example, magnetometer observations,
Right.
radio occultations, as I said. And then there's, many other instruments that study different parts. Some instruments study the magnetosphere and, just the magnetic environment of planets. Other instruments are focused more on the atmosphere, and gravity science and magnetometer, they tell us a lot about the interior structure of the planet.
Indeed. Cool.
So basically, if we draw this parallel, between a possible Uranus mission with Juno and Cassini, what we can study is, for example, one thing that comes to mind is the winds, right? That these missions were able to determine how deep the winds on Jupiter and Saturn are. So it turns out that, for example, for Jupiter, we know that the winds go down to about 3,000 kilometers below the cloud level, and Saturn, they go down to 9,000 kilometers. For Uranus, we have some preliminary results from Voyager 2 that the winds are not believed to be deeper than, between, I would say, 1,000, 2,000 kilometers.
Okay.
So it's possible, we don't know exactly, we don't get a upper limit, we only get like a maximum depth, right? But we are very interested, for example, to understand how these winds behave just below the cloud levels.
Might there be a possibility of dropping a probe in?
Oh yeah, I mean, UOP stands for Uranus Orbiter and Probe. Gravity science in particular is not something that you do with a probe. And the reason is, well, I mean, there are many reasons. I don't think we have the time to name them.
I just threw that in. It's
But,
okay.
you have other instruments that are, very important, that if you drop a probe inside Uranus, you can measure, temperature, pressure, composition, and winds, perhaps.
Right.
This is how probe could be complementary to a gravity science investigation, because from gravity science you get let's say, the ballpark depth, and then with the probe, you can compare.
Detail.
Yes, you can compare like your wind measurements, even though, gravity science does go much deeper.
Yeah.
Because the probe at some point, because of the pressure, it's just going to, what happened to the Galileo probe, right?
Exactly. Pop.
Yeah, but with gravity, you are in orbit around the planet, you can keep going, and you can explore the interior. But, one caveat with gravity science is that even though it's very important and you can constrain the interior model of planets pretty well, the thing is that the solution will not be unique. And so you have, you are orbiting around the planet, right? You get this data, and I will explain later on, I think in the paper, we will go into more details. I will explain how we actually make these measurements, but basically what you're measuring is an external gravitational potential, and then you have an infinite amount of models that can actually match these measurements, right?
Okay.
And so, I mean, it's still going to down select your models a lot. So it's going to constrain your model, right? But there's no there's no way that you will have one unique solution,
Yeah.
and say this is, the only interior model that we can get exactly. So then obviously, then the theory comes to your aid in the sense that, you can compare not only your models with your measurements, but other measurements from other instruments, for example, the magnetometer, or a microwave radiometer, or you can compare it to even just theory. Just some models are just not physically, maybe they match your gravity, but they're just not physically possible. So there is a way to kind of like narrow down, right?
Cool.
And so we always say that, gravity science is highly recommended for a mission, especially one that, it's going to orbit for the first time a planet. It's not only because of science itself, it's also for navigation purposes, right?
Yeah.
You need to know the gravity field pretty well. Yes.
Yeah.
So yeah, these are basically, in a nutshell, our objectives in this study. And now, there are a lot of considerations to do when you're designing an experiment or just proposing an experiment potentially. There are things that are common to every space missions, and then there are some things that are very, very specific to, Uranus and the environment.
Right.
And so basically, things that are common to every planet are, well, you have a budget of mass, you have a budget of delta V. I mean, of course, that is different. It grows with distance, right?
Sure.
But these are things that you need to think about in every mission. Being Venus or Mars or Uranus, you have to do kind of a compromise between the science you can get and then the actual mass that you can put in orbit, right?
Fair.
For
Yeah.
Uranus, you also have the fact that, this is a much more distant body than, other planets that we've explored. Now, I don't want to say something that is not, I think I tell the truth when I say this would be the farthest planet that we ever orbit. Like, of course, we've had New Horizons.
Yes.
Right, but that was a flyby. So, I mean, this would be an orbiter mission. So this, this would be, so it's challenging, and it's not only challenging to get there, it's challenging also, like you're gonna get all this data, all these images, spectrometers and whatnot, and then you have to send this data back, right?
Correct.
So that's, there's also the issue of power, signal to noise ratio.
Yep.
So yeah, and so in this, yeah, exactly. So that's we've had recently a lot of studies for Uranus missions. We have obviously the decadal survey, but we've had also some pre-decadal studies that were led by different institutions. And so they've looked at all of these, scenarios. Obviously, in my paper, like it's not my place to design a mission. So, I'm just taking their output from these studies, what we know, like what the power will be, what kind of orbit is more,
That'll be an interesting one.
likely,
Yeah.
likely to happen. And then we run some simulations where we say, okay, like if this is the what's going to happen, then this is what we can get in terms of gravity science.
Cool. Good. Okay.
So so we can talk about trajectories. One thing that I will say is all of my simulations take place in like late 40s, early 50s. So I think what people sometimes don't realize. I mean, obviously depends on if you're in the field, but the public most likely doesn't realize that space missions take so long, right?
Oh, yeah.
Yeah. So I mean, maybe they do. But if you have a
Decades.
career that spans, I don't know, let's say 40 years, you only have a finite, obviously, number of missions. Yeah, that you can, like, maybe you have one or two that you can follow from, beginning to
Start
start.
to finish, right? Mm-hmm.
Exactly. And so
Decades.
basically, yeah, so these simulations are now we're in 2024, 25, 26 years away.
Yes.
So, yep. And this is considering a launch date in the mid to late 30s.
Okay.
And I know there's a lot of talk about potential Jupiter flyby, not Jupiter flyby. We don't go into the details in this paper. I don't think it makes any difference to us once you get to Uranus and you're burning your engine to get into around the planet. Yeah, you start collecting data, and we're good to go.
Mm-hmm.
Yep. So let's see. So talking about trajectories, I mean, obviously there are so many options that you get there. You could be in many different orbits, but the reality is that we assumed in this paper that most likely we're gonna be in an orbit that we call either Cassini-like or Juno-like.
Okay, love it.
I mean, so one thing that I get asked very often is, I mean, isn't a circular orbit the best for gravity science? And I say, yeah, I mean, it's the best for gravity science. It's the best for every instrument probably, right? But it's very, 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 very expensive. I cannot stress enough. It's
Yes.
very expensive to get your spacecraft into a circular orbit so far away from Earth, right? Because you need an amount of delta V that is very high.
Yeah. Mm-hmm.
So now for gravity science, you do need to be close because we are measuring the gravitational potential. So obviously the gravitational potential is decreasing, like your gravitational acceleration is decreasing with the distance, right?
Yes.
So, and it's not decreasing linearly, it's decreasing with, a power that is a function of the degree. And we will talk about degree, but even in terms of monopole, which is what most people think about when they think about gravity,
Right.
it's going with the square of the distance, right? And so, I mean, obviously you want to be as close as possible to sense the strongest gravity. And that's why circular orbits are always thrown in the middle and say, well, isn't that the best because you're always close? Yes, but if you have to do that compromise that we talked about, compromising what would be best for your science and what is actually feasible and what is actually makes sense, right? So in this, we only consider Cassini or Juno-like trajectories. And this mean that they are very highly eccentric, which means that they get very close to the planet for, I would say, a couple of hours, right?
Okay.
And they spend the majority of their time far away from the planet, right? And by a lot of time, I mean like anything between, I think Cassini was something like 25 or 27 days period. So, you basically, and Juno, was for 53 for a long time. Then obviously after the satellite flybys, now it's reduced, but it was 53 days. So you spend, imagine, 53 days very far away. Well, let's say 52 and a half, very far away from the planet. And then you have a few hours where you're getting your actual data, right?
Data. Mm-hmm.
And so, that brings a lot of also considerations, like which instruments are gonna get the measurements and so on. What's nice about gravity science is that it doesn't require data volume. I mean, it does, because you still have to monitor the health of the transponders. And I think there is, the section after is about the radio science instruments, so we will talk about that. But basically, what happens is that you are relying on the Doppler measurements, and the Doppler measurements is on the radio carrier itself. So you're not really carrying data volume, right? Because you're interested in the carrier itself. Usually the carrier is just a carrier, right, for data.
Envelope, yep.
Exactly, but in this case, we're actually interested in the sky frequency, what we call the sky frequency. So that's a plus. But yeah, one thing is that you have to have your spacecraft antenna that is pointed towards the Earth. So that okay, so does that attitude conflict with other instruments? So you have to have all of these considerations. Right. It's early though to think about this.
Lots of time.
Yeah. So in this study, we have 3 trajectories. As I said, they're all highly eccentric. So we kept the eccentricity of the orbit constant to 0.98.
Okay.
That means an orbital period of 90 days. So that's very long as well.
Okay.
Then we kept the number of orbits fixed. We decided let's go for 8. It doesn't mean that a potential future mission will have 8 orbits or
right, but it's a baseline.
It's just a baseline. It's just a baseline. And we kept, I think these are the 2 parameters that we kept fixed, and then we varied the inclination, we varied the altitude of the pericenters, and something else, let's see, no, velocity of the spacecraft stays the same because the orbital period stays the same. So yeah, I would say inclination and altitude of the pericenters is what, yeah. Oh, I should say, obviously, the other thing that is gonna change, because you're changing other orbital parameters, are the latitude and longitude of the pericenters. And we will see in figure 1, we can go to figure 1, and I'll show you what I mean. Yes.
Okay, we're gonna do.
Yep, so these are the 3 trajectories that we considered in the study. So you have the purple one in order, the green one, and then the yellow one. Okay, they do have all the same eccentricity and the same orbital period, but you can tell that they're quite different, actually.
Yeah, quite. So,
yeah, we start from the purple one.
Mm-hmm.
One is staying outside of the rings. Correct. So this is another thing that, when I started to get interested in Uranus, I realized, oh, Uranus has rings. Because, you obviously think about Saturn, but, Uranus has quite the ring system as well. I mean, it's not as thick as the Saturn one.
Darker.
But it's definitely very interesting object by itself, right? There are people that study rings, and, they make amazing contributions also to I forgot to say, also to the study of the interior. I did a shout out to the magnetic field people, but I mean also the ring people, because the rings, they oscillate with the interior. So, you can look at the rings, and for Saturn, I mean, Cassini did wonderful things, just looking at the rings and inferring about the interior structure of the planet. On the other hand, even though they are wonderful, they are also kind of a hazard, because because I mean, you don't want the spacecraft to fly into the rings, right? Because there would be collisions with particles, and and the densities are very uncertain, especially when getting to the planets, because the rings, they get much more sparse, and they are more difficult to study. And so even from the Earth, it's much more difficult to see them, to study them. And so the reality is that we don't know what is the density of the particles inside, very close to the planet.
Right.
And also, we don't know what's the density of the atmosphere. That's another thing. It's drag, right, on the spacecraft.
Fair, right?
Yeah.
Mhm.
So trajectory one is like a safe option where you decide, okay, I'm staying outside of the
All
ring.
danger.
Yep. And I'm going to observe closer to, I would say the pole, in this case, the southern hemisphere. So you're going to observe closer. I will talk about, what is the downside of doing that. Let's go through the other trajectories. The second trajectory is more like Cassini-like.
Yeah.
As
Mhm.
the inclination is about 45 degrees or 135, depending on, how you're counting it. And it's getting inside the rings pretty
Yes.
close. I think the pericenter's altitude are about 1,000 kilometers.
Nice.
And then lastly, the yellow one is what we call the Juno-like, because on top of being like the green one, it also has the last 4 orbits that are almost at polar inclination. And we will discuss later
Yes.
why that's important. So yeah, so we have like a safe option, we have a Cassini-like, we have a Juno-like trajectory. So if you scroll down here, you can see, for example, one very important parameter for gravity science, which is the altitude of the pericenters.
Yes.
Yeah, you have,
Beautiful.
you have the trajectory one is what you see in the southern hemisphere, so more like around latitudes minus 45. And you can see that you stay pretty far away from the planet.
Okay.
Because you want to stay outside of the rings,
Mm-hmm.
you cannot get as close to the planet as you would like, because otherwise the spacecraft wouldn't be able to kind of do this arch and avoid the rings, right?
Right. Mm-hmm.
And so that's why they're kind of high, around 5,000 kilometers. The trajectory 2 and 3, you can see they're much, much closer, around 1,000 kilometers. But you can see, like,
Yes.
if you look at the diamonds, you can see that they all have this inclination around 45 degrees.
Yeah.
The stars, they have some that are 45 degrees, and then you go closer to the Juno orbit at, 105 degrees or something like that.
Uh-huh.
Yep.
Uh-huh. Okay.
So this is what we call the ground tracks. This is what, tracking
Yes.
the spacecraft from the surface of the planet would look like. As I said, it's very important for gravity because you want to sample the gravity field in a uniform way. So I believe we will talk more in depth about gravity field later on. I think we can now talk a little bit about the instrument if you scroll down.
Sure.
So yep. So let's talk
Radio
about the
science
instrument
instrument.
a little bit. Yeah. So as I said, gravity science relies on the Doppler measurements. On measuring the Doppler shift on the radio carrier. So you originate a radio signal from our ground station. So in this case, we considered NASA's DSN, the Deep Space Network. We have NASA has stations in Goldstone, California, Madrid, and in Canberra in Australia, and Madrid in Spain, of course. So they are about 120 degrees, right, in longitude,
Right.
so
Right.
that you will have observability of outer space at every time of the day, basically.
Cool.
So
Mm.
you have the ground station, it's transmitting a radio signal, the spacecraft is receiving this radio signal, coherently retransmitting it back, and then the ground station that originated the signal is receiving the signal back.
Yep.
And now you have a Doppler shift though, right, on this signal because the spacecraft is moving, right?
Yes.
So if the spacecraft is moving, you're able to measure what we call the line of sight velocity. It's the change in velocity of the spacecraft along the line of sight of the radio path, right?
Yes. Yes.
And then the velocity is related to many things, but one thing that it depends on is the gravity field of the planet, because the gravity field is is changing the trajectory of the spacecraft. Now, for the gravity field, as I said, most people think about the monopole, but the reality is that we also have additional terms than the monopole. So this is what we call spherical harmonics
Yes.
of degree L
Yes.
and order M, well, there are different ways of, of different letters depending on who you ask. I use L and M.
I use LMN.
Yep. So L, the degree, without going into too many details, is the variation along latitude of the gravity field, and M, the variation along longitude, in a nutshell.
Mm-hmm.
So, we don't only want to measure the monopole, we want to, which is the mass, it's the bulk, mass of the planet. We also want to measure these variations along latitude and longitude. That's why it's important when we were looking at the trajectory, it's important where the latitude and longitude of the pericenters are.
Oh,
so
yes.
Going back to the instrument, so, we use the DSN in this study, in this paper. We consider a transponder on board of the spacecraft that is capable of transmitting in X and Ka band.
Cool.
And,
Yes.
pretty much, it's pretty much a standard, I would say, radio science experiment. One thing to consider is that obviously, to do measurements, the spacecraft has to be in continuous communication with the Earth, right? So sometimes we have what we call occultations, which the spacecraft goes behind Uranus. And, that's very interesting in a sense, because you can study the atmosphere by looking, and it's not the subject of this paper, but we do occultation, this kind of occultations with Juno. But, on the other hand, you lose the gravity data, right? Because if you don't have signal, you don't have measurements.
Right.
And so this is another thing that, we need to consider, and we did here.
Cool.
So so this is the instrument in a nutshell. There's much more detail, the level of noise that you can expect. Of course, we assume that we're using the state of the best instrumentation possible, that it's available. It's what, it's what's flying on Juno, it's what's flying on Bepi Colombo, which is a ESA mission, it's what's flying on JUICE, which is the other ESA mission, planetary mission that is currently in cruise. So we assume that, we will have the best instrumentation. Yes.
Cool.
All right. So we talked about the gravity field, I think a little bit. And so this is what I was talking about when it comes to the instrument. We're assuming that we have the best instrumentation with a noise level that is, comparable to what Juno has been shown. And here there are, several references to all the work that me and my colleagues we've done on Juno to characterize the noise. And so we assume that kind of instrumentation. We assume also that, as I said, we are able to observe for plus or minus 3 hours around pericenters, except when you have Uranus occultations.
Yes.
Then you have to consider that. Yeah.
Cool. Okay. Awesome. I'm with you.
Yep. So then moving on to the dynamical model, I mean, we talked a little bit about the gravity field, right? So so we talked about, monopole and other higher degree terms. So special to Uranus, I mean, it's in general for all gaseous planets. So the planet is a hot ball of gas that it's rotating very fast, right? I mean, Uranus, it's about 17 hours, even though nobody really knows, right? It's very uncertain, but it's around 17 hours. So it's pretty fast. I mean, it's less than an Earth day. And it's massive, right? These planets are big. I mean, Uranus is not as big as Jupiter and Saturn, but it's quite large. And the radius is about 25,000 kilometers. And so, as you can imagine, if it's spinning, there's a way that the planet is deformed just because it's spinning so fast that it follows the centrifugal force.
Yes. And
so that influences what we call even spherical harmonics, which is the ones that are symmetric with respect to the equator.
J2, J4, etc.
J6, J8, and so on. Now, the winds, on the other hand, they can be symmetric with respect to the equator or not. If they're not, like for Jupiter, right, that this is very, it's very evident if you look at the wind profile of Jupiter, then not only you will have some contribution to the even harmonics, you will have a contribution to the other harmonics.
Yes.
And the nice thing about that is that you can use other harmonics to study the winds because they're not compromised by the uniform rotation, right? Because those, it's only for the even harmonics. They don't contribute to the, so all is purely winds, right? So that's you know, at the basis of, you know, studying what has been done with Juno and what has been done with Cassini and what we hope to do for Uranus. So yeah, if you go to figure 2, yes. So, and 3, actually, we can talk about figure 2 and 3 together. So, you know, in order to make our simulations, we have to assume like an a priori gravity field for Uranus. And again, this is not to say that this is the interior model of Uranus. It's just a, you know, a good interior model that matches the Voyager measurements of J2 and J4 that was done with Voyager 2. And this is, you know, a polytrope, and you have a discontinuity of the polytropic index at about 0.8 of a fractional radius. So that means basically that the slope is changing. You know, you kind of, it's changing around 0.8.
Yeah.
And, you know, you know, this is the work of one of my co-authors, Chris Mankiewicz, but, you know, I understand a little bit about, you know, doing interior modeling. And, you know, this is a polytrope, which means you're kind of agnostic about, you know, composition, you know, energy balance, all these nice things that, you know, other people that do more of like theory of planets, they are taking into account. In this case, it's like, let's be agnostic. And all that we are assuming is that the density and the pressure are going to be related by some kind of relationship, which I think it's probably equation 1 of the paper.
Yeah, that's fine. Straight out polytrope, and here you go.
Yes. So that's all we're assuming. And the other thing that I said, the requirement is that it does match the measurements of J2 and J4 for Voyager.
Right.
Okay, so this is for the background, what we call the background hydrostatic density, right? On top of that, if you look at figure 3, we are superimposing some winds profile, okay? So again, we don't know exactly what is the depth of the winds. So here we take 2 models. One is shallow, as you can see, it's on the left. You know, you have your surface winds that they're from Stromowski et al. 2015. We get, you know, from ground-based observations, we get the wind profile, and we just how do you say, we project it on into the interior, right?
Yes.
And on the other hand, and you decide what you want to project it. And the same thing for the right one, but it's much deeper. So the one on the left is of the order of a few hundred of kilometers, and the other one of a few thousand of kilometers.
Okay.
We know for Voyager 2 that the truth would probably be, we would probably be in the middle.
Probably.
Yeah, so now if you go to figure 4.
Okay, we got profiles, interior profiles, winds.
Yeah, so figure 4, now we have our interior model, we have our winds, we can make predictions of what the gravity field will look like. Now, this is not, you know, this is only to compare it to the accuracies that we will get with our simulations. Because if we have an idea of what the order of magnitude of the gravity field is, then we can say, oh, okay, we can compare it to the accuracies that we get, and we can say, okay, maybe we will see J8 or maybe we'll see J6. So that is the idea.
Nice.
Plot, so the black diamonds, they are the measured gravity field of Uranus by Voyager 2.
Okay.
You know, full and empty symbols are negative and positive and negative, because this is a log scale. So you know, if you want to plot negative values, you have to give it like a legend. And then the black stars are the predictions for the even harmonics that we talked about, coming from the interior model that we used.
Okay.
And then the red and blue dots are the predictions for the winds. So the shallow winds are in red, the deep winds are in blue. So basically what this plot says is, we don't know how deep the winds are, but it will probably, their magnitude will probably be in this shaded area, right?
Right.
So now if you look at J2, J4, and in a sense, also J6, you see that what determines their value is mostly the uniform rotation, but then as the degree increases, it's less and less important. For the wind,
Yes.
it's the opposite, like J2, J4, it's less important, and then J6, J8, it starts the contribution from the winds, even for the even harmonics, it's pretty hefty. And so the idea is, okay, if we can measure up to J8, potentially we can decouple pretty well the effect of the winds from the effect of the deep interior. Yeah,
Yes.
so now
Okay.
this, if you,
Mhm.
yep, if you, I don't know if you have any questions or we
I'm
can.
good right now. I'm following you. I'm good.
So then I would say let's move on to figure 4 and talk a little bit, sorry, 5, and talk a little bit about tides. If I remember correctly, that should be the next one.
It's grabbing that. There's our 30 equations on JLs.
Yeah, so yeah, I'm gonna talk about tides, yes. Okay,
Tides.
so,
Yes, indeed.
okay, so now let's talk about tides. So tides are, usually you think about moons, for example, right? On Earth or terrestrial planets, you say, okay, the tides on Earth, you have tides on other planets. But it's happening also on gas giants. Gas giants experience tides as well. And this is because you have moons that are orbiting around the planet. And so they are raising tides as they orbit, right? And they're changing the gravity field of the planet. And
Indeed. Yes.
yeah, because they are raising these tidal bulges, and we know the periodicity, and we can measure them quite accurately.
Well,
Yeah, so the reason is that, I mean, a planet, let's say a satellite is raising a tide on Uranus, in this case, Ariel, right?
okay. All right.
So I mean, all of them potentially can raise tides, but it depends on how massive the moons are and how distant from the planet are. So if you scroll down a little bit, there should be equation 2, I believe, or 3.
Yeah, I think 2 is up
Yeah,
here.
exactly. So there is this parameter, equation 4, I think.
Or mass ratios.
Yes, yeah.
Okay.
Yeah, so there is this tidal parameter QT that, as you can see, is a function of the ratios between the mass of the moon and the mass of Uranus. And the cube of the ratio between the mean radius of Uranus and the so how distant the moon is, semi-major axis A.
Yes.
So basically what this says is that if the moon is either very massive or very close or both, then it's gonna raise a big tide on the planet itself. So for example, if we go back to figure 5,
right, let's go back to figure 5.
Yeah, let's look at Jupiter, which are the 4 orange dots. I try to use like the color palette of each planet.
Yeah. Very good.
Yeah, you see that Io is raising very strong tides on Jupiter, and that's because Io is pretty massive. It's not the biggest Galilean satellite, but it's very close. So it's raising, and it's pretty massive. So it's raising big tides. For Juno, the majority of the tides that we see, they are from Io. Something for Europa as well. Perhaps like a very, very subtle, yeah, you need a lot of measurements of the tides to be able to, and very precise ones, to be able to decouple the effect from Io of Europa. Mostly we're seeing Io. For Uranus, if you see, which is in the rectangle, you have Ariel. It's actually the third in terms of magnitude in the outer solar system, because you have Triton for Neptune before that. But its effect is actually bigger than Titan, and its effect is actually bigger than Europa as well, even though with these big dots, it's not easy to see, but it's around 10 to the minus 7. So we expect, this is a calculation that we did before even starting the simulations, because we wanted to see, is this like something that we can do? And it appears like, yes, I mean, obviously we were able to do it for Io. We might be able to do it for Triton in the future. we can do it for aerial as well, because the effect should be detectable.
Right.
So but this is only one piece of the puzzle. If you go to figure 8,
Figure 8. Let's go to
which
figure
is just down. Yes, sorry, it was just down from the
6.
other. Yep.
6.
Yeah, so it's only one piece of the puzzle. The other piece of the puzzle is, well, I mean, yes, Ariel is strong enough to raise tides on Uranus, but if the spacecraft is not in the right place in the right moment to measure the tides, then we're not gonna get it with Doppler measurements, right?
Right.
So in this plot, basically you have, imagine that, so Uranus is at the center.
Okay.
And where you get 0 phase to your right, yes, that one, that is the direction of Ariel, always. I know that it's not fixed in space, but imagine that this reference frame is following Ariel around.
I'm with you.
All of these dots, these are the 8 pericenters of each orbit. And it shows then the tidal phase of each observations compared to the position of Ariel. So imagine that Uranus is being deformed along, this line where, Uranus aerial direction is exactly that line, the horizontal in this case.
Yes.
Becoming like, some people call it like, I don't know, rugby. Some people call it cigar shape. It's an ellipsoid, right?
Yes. Yes.
So the idea is that you want to measure, you want to sample different phases, different angles of this ellipsoid, right? They have to be well distributed. So for example, if all of these dots were, I don't know, 90 degrees phase angle or 270, we wouldn't be able, because right, you can, if you have all the points in one or let's say you have, 4, I don't know, let's say each orbit has 8 pericenters, right? You have 4 dots around 90 and 4 dots around 270.
Okay.
Imagine you can match any ellipsoid, you can
2 points. Yeah.
exactly any eccentricity of the ellipsoid. It can be a circle, eccentricity 0. It can be, very deformed that you wouldn't know, right? Because they all pass through these 2 points. But if you have more points, you can constrain the shape much better. So this is the idea.
Absolutely.
And we found that actually, all of the trajectories actually have a pretty good distribution, with, perhaps 2 and 3 being a little better than trajectory 1.
Right.
They're sampling more phases, especially close to 0 and 180. They're very important, right? So we expect to have better results from trajectory 2 and 3, but we will talk about it in the results section.
Cool. Okay.
So all of this that I
Nice.
described, let's say in the last 15 minutes, it's our dynamical model, right? This is our best knowledge of Uranus that we're putting forward for our simulations, right? Now we have to do the simulations themselves. So to do the simulations, let's see. What is, tidal pair? No, we can go to the next section, I think.
Just
Probably
sort of
4. Yep.
see, let's go 3 simulate processes.
So what we do is we take our best knowledge of Uranus and the Uranus environment, and we integrate the trajectory of this potential spacecraft.
Right.
And we get an answer by saying, this is what mission designers do as well. They take, their best observations of Uranus, and they say, okay, if we believe, this gravity field, these tides, these rotational parameters, and so on, this is how the spacecraft would behave around Uranus. And we do the same thing here. Now, but, the extra step here is that on top of that, once we have this trajectory, we can simulate Doppler data on top, right?
Yes, right.
And we assign it a noise level that we think it's, reasonable. Like, for example, in these simulations, we're using the Juno number. So we're saying, we have these trajectories. Yeah, if we have this trajectory 1, 2, and 3, and we have noise level like Juno, what are the accuracies on the gravity field and tidal parameters that we can get? So this is the idea.
Cool.
And when we do that, we want to solve for a set of parameters that we call solve for parameters. Basically, you're saying it's a least square filter where you're taking all of the Doppler data and you're reducing it. It's a reduction. It's a numerical reduction following the least square algorithm, where you're saying, okay, if you have all of these observations, and imagine you have, let's say, each pericenter, we use 60-second data, and we have around, we said 3 hours, we said plus or minus 3 hours, so you have 6 hours. So if you do 6 by 6, you have, I don't know, almost 4,000 observations, and then multiply that by 8, it's, I don't know, 32,000 or something. So you have these 32,000 data points, right? And from those, you are trying to solve for a set of parameters, for example, the gravity field, but there's also the state of the spacecraft. And I think if you go to the table, there should be a table.
There we go.
Yeah, we can skip this one. Yeah, table 2. Table 2, you're trying to use all of these observations that you had, these 30,000 plus, to solve these parameters, which are, we call, solve for parameters, and they can be the spacecraft state vector. So you want to know what the spacecraft is.
Indeed.
You want to know, what is the mass of Uranus, what is the right ascension and declination, the gravity field that you see there, J2 to J25. This is what we wanted to, determine. It's a little bit conservative. I will talk about it during the results.
Right.
Then the tides, and, and these are what we call estimated parameters, that you have these constant parameters, which are things that we're not interested right now to estimate, but we still want to acknowledge that we don't know what these parameters are, and we need to include their uncertainty in our estimation. So this is something like the state vector NGM of the satellites. I mean, we have pretty good satellite ephemeris, but it's we don't have a lot of observations in their Uranian system. Uranus rotation rate, which we talked about it, we can't estimate it with gravity field.
Right.
And, maybe if we have time at the end, I will say a few words about it. Okay. But its uncertainty is still affecting our measurement. So in this case, we put a very, very large uncertainty. If you look at that, that is almost 100% uncertainty. Like we
don't know.
if you take a central value of about 17 hours and 24 minutes, which is what the ballpark, then we're saying, okay, it could be anything from 0 to 34 hours, we don't know, because this is what the IAU is saying. It's currently the uncertainty is more than one full revolution. So that's why.
Yeah. Okay.
And then, we consider other tidal parameters, some are non-gravitational, the GM of the rings, that's important as well. And then if you scroll down to the next figure, we combine all of these informations to understand how precisely we can determine the gravity field of Uranus, right? So, okay, this is a lot, so I will try to go over it in a coherent way. Okay, so actually the blue and red line you already see. This is our prediction of what the gravity field of Uranus would be, depending on which wind profile we're using. So it will be inside, somewhere between these two lines in the shaded area. That's where we think the real answer will be. And the black solid line, these are the Voyager 2 measurements from Jacobson 2014. So that's our best knowledge of Uranus gravity field right now. And then the dashed line, these are the uncertainties that we think we can get with the 3 trajectories. Now, there are 4. So the first column, you will see that it's labeled OC, and then the second column is no OC, right? So what does that mean? That the first one doesn't have a occultations. Sorry. The first one, the left one, is occultations. The second one doesn't have occultations. Now, by design, only trajectory 2 and 3 have occultation. So you will notice that in the left column, the purple line is missing because there's no occultation case, right?
Right.
Then for trajectory 2 and 3, between the left and right column, what changes is that in the first column, we have occultations. And then in the second column, we are preceding the orbit by 180 degrees, so that now all of the pericenters are visible from the Earth. So this is the difference between the two columns. Okay. Now, the 2 rows, you will notice one is Jupe-like, the other one is Sat-like. Okay, so this is a whole other paper, okay?
Right.
Basically, what we
Yeah.
found, what we found at Jupiter and Saturn is that not only internal oscillations are, are seen in the rings, but also they affect gravity, the gravity measurements as well, because these internal oscillations that are called normal modes, and I know that you talked to Chris about this. They not only change, as I said, they don't not only excite the rings, but they also change the gravitational potential of the planet.
Yes, they do.
So
Stop sloshing around.
exactly. So I mean, this is unfortunately just for the study of the zonal field is a little bit of a noise source. I mean, normal modes are very interesting in their own, on their own. But if you want to study the zonal field of a planet, then it's a little bit of a noise source, because normal modes are very dynamic and unpredictable in a sense. So imagine that you are basically adding noise to your observations.
Okay.
Now for Juno
Sure.
and for Cassini, the accelerations that they were sensed by the spacecraft due to normal modes are I should say due potentially to normal modes, because we don't know if, I mean, we suspect and we think we have pretty good evidence, but it's hard to say if you don't have a way to determine uniquely that, okay, this is normal modes, right? So it could be potentially another source of acceleration.
Fair enough. Mm-hmm.
For Saturn, actually, it was detected to be much stronger than Juno, about 20 times. So we have the first row is Jupe-like, which is less intense normal modes, and then the second row is Saturn-like, which is more intense normal mode. So you see that uncertainty is always higher for the Saturn.
Yeah. Mm-hmm.
Yeah. So now let's go through the results. I mean, maybe I would start from the right column, which is, not what you would expect. Let's start from the no occultation case, because you have all three trajectories.
Mm-hmm.
Okay, unsurprisingly, you get the uncertainty improves as a function of the number of trajectories. So you have trajectory 1, it's the less accurate trajectory. Trajectory 2, and then trajectory 3 is the best, because not only is very close to the planet, but it's also polar.
Yes.
And polar, why is that important is if you're polar, you're sampling a lot of latitudes.
Yes.
And what is the zonal field if not latitudinal variation, right? So that's why it's the best option in this study, right? Because you're sampling your range of latitudes is very wide. Still, trajectory 2 is pretty good. If you go down to the Saturn-like case, it's the same, except the lines, are increasing by, I would say, an order of magnitude, which maybe slightly less, which we would expect, because the accelerations are about 20 times.
Okay.
Bigger.
Right.
So you do expect, uncertainty there are around 20 times bigger. So everything is translated a little bit upwards.
Yes. Okay.
Now, if you look at the occultation case, so for trajectory 2 and 3, the spacecraft actually goes behind the planet, you see that your uncertainties are much degraded, because you're missing data in that crucial moment where the spacecraft is very, very close to the planet. Right. And so they are significantly translated, especially in the Saturn-like case, because not only you have occultations, but you also have the highest level of noise. So actually, in the bottom left, for you can improve J2 and J4 compared to Voyager 2, but you can't really improve J6, right? Which is very important. So I mean, the take-home message is, if you're gonna do gravity measurements, try to avoid, occultations are important because you want to study the atmosphere, but try to do them not at close to pericenters, but maybe close, when the spacecraft is farther away.
Right.
The other takeaway message is, normal modes we don't know what normal modes are on Uranus. And, maybe we will talk a little bit about that at the end, but, that is also a very interesting study. So it's possibly they will be as intense as in Saturn. We don't know. We just don't know. So let's look at the best case scenario, which is the Jupiter-like trajectory 3 case. So this would be the right top plot. Let's look at the yellow dashed line. In this case, this is important to highlight that and actually this is true also for the Saturn, like, so the yellow line in the bottom right.
Yes.
We might be able to get J8,
Yeah.
J in this case. So if the spacecraft is in trajectory 3, regardless of the intensity of the normal modes, we might be able to get J8, and this is very important not only for the winds, but also very important for the interior structure as well. So we might be able to decouple the two effects.
Nice, nice. Okay.
Okay, now if we move on to figure 8,
Cool.
so with the next one.
Okay, figure 8, zonal gravity fields and
So this case is,
zonal harmonics.
yeah, it's one of those 4 plots. So in this case, it's the Saturn like
Okay.
without occultations, and
Okay.
for trajectory 3.
Okay.
So the uncertainties that we saw on figure 7, those were at the end of mission, so after all the 8 orbits. In this case, I'm showing how it improves at adding more data.
Got it.
You
Good.
can see that, if you only have 1 orbit, I mean, again, the solid black line is the Jacobson line. There's
So you
improvement.
want to go below that.
Yeah, you want to go below that, exactly. And by the way, you might ask, oh, why is the Jacobson measurement so good? I mean, it's Voyager 1, only the one flyby. Well, the reality is that he's adding other types of data. It's not only radio. So this is only, I mean, the dashed yellow line is only radio.
Okay, good.
He's adding also the satellite data, astrometry data, so he has more constraints. Yep. And so, same for 2 orbits, 3, 4, 5, you start to see, okay, 4 is compatible to, what the Jacobson measurements. 5, you see that we're still doing better. There's a chance that we might get J6 depending on the depth of the winds. And then you see that 6, 7, 8, there's not a I mean, there is a significant
There's an improvement,
but the improvement, and this is a known fact, I mean, the improvement is going as the square root of time, or the square root of the number of pericenters. So this means that the more pericenters you add, you still gain information, but the information is less dramatic than the improvement is less dramatic than at the beginning. So this plot is, I mean, the takeaway message is we want to have at least 6 to 8 orbits around Uranus if we want to know the gravity field better than what we already know, right? All right, so then now let's discuss tides. We're still discussing the results, so we can go to figure 9. So we leave the zonal field. We discuss tides. And
numbers, yes.
Yeah, so using the same trajectory, so the color code is the same. Purple is trajectory 1, green is trajectory 2, and yellow is trajectory 3.
Lovely. Okay.
Now you see this is the 3 sigma uncertainty on K2. So K2 is what we saw earlier, is number that is describing the tidal deformation of Uranus.
Yes.
So now I should say there's a reason why we're so interested in K2, and the reason is that there was this study in 2021 by Lars Stixrud from UCLA that they predicted that the value of K2 for Uranus would significantly change based on whether the core is frozen and solid, or if the core is more like diffuse or liquid, like in the case of Saturn and Jupiter, right?
Sure.
So there is this talk about frozen core. So the dashed black line that you see here, that is difference. It's the delta K2 that you would see between a frozen core and a liquid core. Okay.
Thank you. Good.
And then the bars of the histogram, these are the 3 sigma uncertainties from our simulation. So basically, if our uncertainties are above this dashed line, which is the delta K2, we have insufficient precision to determine the core state, because we will not be able to distinguish between a K2 of 0.28 and a K2 of 0.36, which is Lars is predicting 0.28. So the lower K2 is for a frozen core, and then the higher, because the K2 increases with, let's say, I mean, obviously if it's a liquid body, it deforms more than a solid body, right? So we expect expect K2 to increase. So 0.36 would be for a liquid core. And so if our uncertainty is above, then there's no hope to distinguish the core state. If they are below, then we might be able to say something very important about the interior of Uranus. So you see that in the case of trajectory 3, which was our best case for zonal harmonics, don't have occultation, we get more or less the same results. If we don't have occultations, then that is still our best case scenario. If you look at the last bar, right, you have the lowest uncertainty. So that would be trajectory 3 with no occultations, with normal modes as intense as on Jupiter. For trajectory 2, surprisingly, which was our second best, right, for zonal harmonics, you get actually very good uncertainties as well, and there are more uniform across the board. And the reason is that you remember how for zonal harmonics, the latitude is important. For K2, the longitude is important. So trajectory 3, which has at the end polar orbits, yes, you are sampling more latitudes, but you're not sampling a lot of longitude, right? Trajectory 2, it was at 45 degrees. And so you still sample latitude, but you also sample longitude. And that's why we get pretty good results for trajectory 2. Trajectory 1, I mean, we don't have occultations there. So we found that also surprisingly, if the normal modes, I mean, if the normal modes are very intense.
Okay.
You see, in this case, you see that the intensity of normal modes has the largest effect. Yes. So, but if they are less intense, so let's say a Jupiter-like scenario, then again, because and we would have to go back to figure 1, because the longitudinal coverage was pretty good, you still get a pretty good K2. So we found in our simulations that in 70% of the cases, we would be able to determine K2 with the precision that we want.
Okay.
So yeah, these are the main results. I mean, of course, these are simulations, so there are caveats to simulations. For example, normal modes is not something that it was predicted would happen at Jupiter and Saturn, except actually there is a 2017 paper by some of my Juno colleagues that predicted that actually this noise, in a sense, because if you're studying the zonal gravity field, it's a noise source, would affect the measurements of the gravity field. And so, yeah, I mean, just like normal modes, there could be many other things that we don't know are happening at Uranus, right? It could be, we get close to the planet and the atmospheric drag is jeopardizing our, or putting noise on our observations. It could be, yeah, you never know until you get there. But so this is our best guess of
Very cool. Very cool. Very cool. So if you could wave your magic wand, which trajectory would you take?
Oh, I would take trajectory 3.
Okay.
I would wave my magic
A little riskier, but love it.
Yeah, I mean, I talked to other people that are Uranus scientists, and they're like, "Why only 8 orbits? Let's do more." And I'm like, "Yeah, I mean, eight.
Sure.
We're saying that 86 to 8 is the minimum that we would require.
Right.
For example, for the magnetic field, you need at least 16 because you want to sample. At each for magnetic field measurements, longitude coverage is very important, right? So you want at least 16 longitudes, right? So there are other considerations. It's not only gravity science, of course, right? So yeah, I mean, we will take what we can get for sure. Yes.
Absolutely. Lovely. Marzia.
Oh, I'm sorry. One other thing that I wanted to mention is we talked about normal modes as a source of noise, but again, normal modes are also very interesting in their own sake.
In their own right. Yep.
There are other studies going on in parallel. We are asking, can we use gravity science to detect normal modes?
Yeah.
So that is a whole other paper.
Very cool. And we're going to come to that. Marzia, I want to thank you so much for walking us through your very awesome article. Lovely.
Thank you. Thank you for having me. It was fun.
Sure. And you touched on it a couple of points. And so let me just ask, where do you think we go from here, given the published article? So is there additional data sets one could bring into the pre-analysis beyond radio? Other analysis techniques and so on. So what's your sort of next steps on our voyage to Uranus?
Yeah, so I think it's very important now that there is so much excitement about ice giants that we continue to run simulations, to run possible mission scenarios to see what actually we can get at Uranus, so that we as a community are as ready as possible, for this mission when it will happen. So, I mean, as I mentioned, I think, and I'm already collaborating with people from UCLA and University of University of Texas at Austin,
Yep.
to understand what we can do when we combine gravity field measurements with magnetic field, because magnetic field also you measure with spherical harmonics, right? So there's a lot of potential for combining these two types of measurements.
Mm.
Also, thinking of my Juno experience, I mean, the microwave radiometer is also an instrument that we want to look into and see what it can do to study the atmosphere of Uranus. I think 3 years ago, we had a combined set of papers where we studied the Great Red Spot with gravity and microwave radiometers. And that was very interesting. That showed how you can combine, these two types of measurements. I think on Juno, there's also a lot of work on the polar vortices, combining red imaging, and then of course the rings. We really want to know about the rings. Like, can we use the rings of Uranus like we used the rings of Saturn? I mean, that would be great. And there are people that are looking into that. So that is a great complement to gravity science.
Cool. Very good. Well, it's going to be very exciting to see this develop over the next couple of years as we will go to Uranus. Go, go, go. I can say that. I can say that.
Uranus, yes.
So very good. It'll be awesome. Marzia, I want to thank you so much again for walking us through your very lovely article.
Thank you. Thank you for having me.
Sure. And that will do, everyone. And I hope this made your Uranus Day and Astronomy Day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.